The name of today's lesson is Properties and Operations. Operation is a word you're familiar with. You know that it has to do with what we do to numbers when they are in expressions and equations, adding, multiplying, subtracting, and dividing. Let's take a look at our vocabulary. We have a few, and they're going to take up a few different boards. First, we have the commutative property. This will hold for both adding and multiplication. And what it means is that when you're adding, if you move the addends within the expression, your sum won't change. Likewise, during multiplication, if you take the factors and put them in a different place within the same expression, your product won't change. The way that I used to remember that when I first learned this was that when you are commuting, you're traveling somewhere. And so if these pieces of your expressions travel within the same expression, nothing changes. And here are two examples to show that. Here we have a positive 6 plus a negative 11, which we're showing is the same as if you move the position, move the addends, and make it a negative 11 and a positive 6. You'll see, no matter how you combine those integers, you end up with a negative 5. Same happens with multiplication. Here we have a negative 12 times 5. Those are our two factors. On the right side of the equal sign, we're just changing the position of them. So we have a positive 5 times a negative 12, and both times you get negative 60. Our next vocabulary word is the associative property. This again applies to both adding and multiplying. And what this says is that you can group your addends or group your factors in any way that you want, as long as you are working with the same terms. The way I remember that is when you associate, you have people that are close to you, so you can group they're the people in your group. So you can group your numbers in any way and still have the same answer. Let's take a look at the addition example. We have 6 plus 3 plus 1. Now that's a pretty simple fact, and I know that you already know that that equals 10. But the associative property shows that if you wanted to, you could group two of the addends if that helps you to get to your sum faster or more easily. Here's an example with multiplication. Here we have three factors, 4 times 25 times 6. And sometimes you'll see this with a grouping already made, and sometimes you'll see this with no parentheses, just the factors in the expression. But what I did, because I found, for me, what's easier, is that I noticed that we have a 4 and a 25. And I know that you know right away that when we multiply 4 and 25, we get 100. So another way to look at this expression is to see it as a 100 times 6, which equals 600. And if you were to keep this as it was on this side, you would get the same thing, only you would end up with 4 times 150, which is 600. But for me, this is friendlier, making the 100 first. Now here we have our third and fourth vocabulary terms for this lesson. We have the additive identity and multiplicative identity. Identity here is the key words. What might help you remember is that your identity is who you are and what you look like. And so these rules have to do with applying a number to an original number, but not changing its identity, not changing what it is. When we're talking specifically about the additive identity, we're just saying that any number added to 0 keeps its identity. So any number plus 0 equals itself. And as you can see here with 3 plus 0 equals 3, a negative 11 plus 0 equals negative 11, and b plus 0 equals b. This applies to positive and negative integers as well as variables. And then our multiplicative identity means that any number times 1 equals itself. It retains its identity. And again, it works with positives, negatives, and variables. So now what we're going to do is use these properties and identities in solving our examples. Let's take a look at this first one. Evaluate the expression. Now, some of you might find it much more easy to go through and from left to right add all the numbers because you can see that they are all positive integers. But what I'm going to do is use both the commutative and the associative properties of addition to find a friendlier way to get the sum. So what I'm going to do is take this 8, because I see that an 8 and a 32 will very neatly make a 10. And I'm going to use the commutative property of addition to move that 8 closer to the 32. Now what I'm going to do is apply the associative property by joining the 32 and the 8, because for me, that very easily makes a 40, and I like that. Then we bring down our positive 16, and the value of this expression is 56. Okay, now, for example 2, simplify these expressions. If you take a look at this first one, I've already done all the math. We have a positive 4 and a positive m, and we're combining that with a negative 6. So in using the commutative property of addition, I moved this negative 6 closer in proximity to the positive 4 because I know that I can combine those two terms given that they're integers. So my next expression becomes 4 minus 6 plus m. Then I recall my rules for combining a positive and negative integer, and I remember that I had to subtract the two numbers. There's my 2. And since the 6 is a higher number and it's a negative, that makes it a negative 2 and our positive m. So this is simplifying this expression. Remember, simplifying is not the same as solving. It might feel a little uncomfortable for you to have this feel unfinished. But since we don't know what the value of the variable m is, this is the simplified version of this expression that we can get. Now, if we look over here, again, I worked out the math. We have a negative 5 times 18x. And just to remind you, when you are multiplying a number, an integer, times a coefficient and a variable, what we do is we multiply the two numbers. So we have a negative 5 times 18, which gives us negative 90, and the x just comes down. So this simplified is negative 90x. Now in our third and fourth examples, we're going to deviate a little bit from these properties. And what we're going to do is apply them to conversions. We'll be doing a lot of this in pre-algebra. First, you might see something like this, that you need to use a conversion fact to change miles into feet, specifically 4 miles into feet. Now, it would be helpful for some common conversion factors like how many feet or how many yards are in a mile if you were to commit them to memory. But lucky for you, we have Google and you have a chart in the back of your books, and you have a lot of resources at your fingertips so that you can very readily find out that in 1 mile there are 5,280 feet. And I'm going to use this information to find out how many feet there are in 4 miles. And what this becomes really is just a case of making an equivalent fraction, which I know you already know how to do. Let's take a look at our numerators, because here is where we have all the information that we need. When we go from 1 mile to 4 miles, what we're doing is we are multiplying by 4. So then, given that these are equivalent fractions, that means that whatever we do to the numerator, we have to also do to the denominator. So what we need to do now is multiply 5,280 feet by 4. And you know I'm a stickler for showing your work. Oops, I made a mistake. And we find out that in 4 miles, there are 21,120 feet. Now, I don't know if you know this, but the United States is one of the only countries in the world who does not use the metric system as our standard unit of measurement. So, given that, especially since the metric system is the language of science, what we'll encounter sometimes is having to convert across the units that different countries consider their standards. So here's one example if we wanted to know how many grams there are in 9 pounds. This conversion is going to be a little bit more complicated for a number of reasons than the conversion we did in our third example. First, I want you to take a look at this. Here's our conversion fact, that in 1 ounce there are approximately, notice the wavy equal sign, there are approximately 28.35 grams. So there's one fact that we need to keep in mind. The other fact that was much more common to us is that there are 16 ounces in 1 pound. Given this information, now we can set up our conversion fact, at least the first step of it. I set up my fraction first with our ounces on top and our grams, our equivalent grams on the bottom in the denominator. And what I did was I set up the second fraction, our equivalent fraction. And we know about the 16 ounces, so I put that in the numerator because here in our first fraction, ounces is in the numerator. And I went ahead and I did this math already. And here's what I did. I saw that to go from 1 ounce to 16 ounces, I had to multiply by 16. And you know that in order to for fractions to be equivalent, whatever you do to the numerator, you have to also do to the denominator. So I multiplied 28.35 times 16, and what I found was that in 16 ounces, which is 1 pound, there are approximately 453.6 grams. We're not done yet. We have one more piece to take care of. We still have to answer our question. How many grams are there approximately in 9 pounds? So what I do is I come back here, we see that there are approximately 453.6 grams in 1 pound. So in order to find out how many there are in 9 pounds, I do the multiplication. 9 times 6 is 54, carry the 5. And I get 40824. I remember to count this 1 decimal point. Here we go. 4,082.4 grams, approximately, in 9 pounds.